Hello everyone. It's a great honor to be with you. I'm Jaecheon, the presenter from the Samsung Electronics. I will introduce this presentation. The title is an efficient method to verify dynamic IP clock frequency on SOC level by using auto-generated active clock monitor. I explain what it is and how it was applied in the SOC project. The presentation will be started with the motivation of this proposed methodology, and then I will introduce the major points and implementation of this methodology in sequence. Finally, I will show the result and the conclusions. The number of IPs in SOC design is increasing to meet market demands on various user applications. So the clock tree is getting more complex to provide desired clock frequency for its numerous IPs. And also dynamic frequency scaling, which is one of the low power schemes, requires numerous IPs clock frequency change depending on DFS level. These things require verification to check whether the clock according to the DFS level is generated for each IP as intended. This means that dynamic IP clock frequency verification becomes more difficult as the number of IPs and the DFS level increase, because even if only a few errors occur, there are a lot of absolute errors to debug. So we need to find efficient method for it. Actually, we are using general debug method for clock debugging when clock is detected. It's to dump waveform and trace CMU components to check the value such as divide ratio and box selection. The figure in this slide simply shows the trace of CMU component values with waveforms for clock debugging. Usually, we start debugging from where the clock is detected, but sometimes it may be faster to start tracing from the clock source. However, we can realize it when we bind the root cause. It makes an inefficient debugging time. Actually, the waveforms take a long time to be dumped, and trace debugging can be taken a lot of time due to the complicated clock tree. And in result in taking a lot of time for verification turnaround time. We considered two things to solve the challenge mentioned in the previous slides. One is to use log analysis for clock debugging rather than waveform to reduce debug time. The other is to provide meaningful debug information rather than just raw data so that user can debug the complicated clock tree efficiently. So we proposed the active clock monitor for efficient method. And the figure in this slide simply shows the behavior of the active clock monitor. Actually, the clock monitor can be used in general for clock verification for purpose of checker or debugging. But the active clock monitor is more specialized in debugging among the purpose of the monitor. It always checks the IP clock frequency and status of CMU component value. And it prints the IP clock frequency in the log along with the change factors such as divide ratio and box selection whenever IP clock changes. So we call this active clock monitor because it monitors the clock frequency considering the relationship between CMU components and IP clock, rather than simply monitoring the clock. The log example of the ACM shows how the ACM works when the CMU component value changes according to steps 1, 2, and 3. It also provides an IT hierarchical path so that the user can know which block the CMU component is in and what module name it is. It's not shown in the example, but if only the IP clock has changed without any CMU component value change, it means IP clock has changed just by clock source. So we need need to monitor clock source as well as CMU components in the block. In order to implement the functions mentioned in previous slides, the active clock monitor had to monitor the status of all CMU components between clock source and each IP clock, because the ACM needs to know which vector changed the clock. To do that, we need to have database described about the relationship between IP clock and CMU components. Actually, I cover this database in more detail later. The video in this slide shows the overview of binding active clock monitors. The ACM is based on interface and it has to bind to CMU components. One ACM covers one IP clock, so the ACM exists as manage the number of IPs. The ACM always checks the IP clock frequency to detect frequency change. Basically, the frequency is calculated by the difference between the rising edges. This calls to considerations to measure the exact IP clock frequency. One is to consider clock gating period by gate component, which is generally used to reduce power consumption. We should avoid frequency calculation while clock is gating by monitoring the gating enable signal like the figure in this slide. So the ACM monitors all gating enable signals associated with each IP clock. The other is to consider the period while mux selection or divider ratio is changing. We use the status signal to indicate that the dividing or mux selection is done to avoid wrong frequency calculation. So the ACM monitors all mux and divider status signals associated with each IP clock. The figure in this slide shows the ACM interface example code. It has many IT hierarchical paths of GM components and IT signals to get values and print IT hierarchy. This binding is auto-generated by clock information database. It is including the clock tree and IP clock information. The parameters of this interface are used for printing the hierarchical path of the modules and indicating the number of the CMU couples between the clock source and IP clock. The basic operating principle of this ACM is that when IP clock is changed, is to bind one of the related CMU couples that changes the status. As I mentioned earlier, the database which indicates the relationship between CMU components and IP clock is the most important point in this proposed methodology. We are using YAML format for database. YAML format was used to include various design information with high readability. It contains all the structured contents of the complex clock tree, and it makes it easy for end user to understand. And it allows the verification environment such as ACM bind to be automated. The figure in this slide shows a simple example of the relationship between CMU components and IP clock. It describes the properties of CMU components in the block and the IP attribute which is connected to the output of the CMU components. It indicates that one block has a mux, divider, and gate named mux B, DVC, and gate D respectively. We can note that the mux B and DVC are connected, and the DVC and gate D are connected through the clock in, clock out properties. In case of IPE, the clock source comes from the gate D output. This means that the gate D and the IPE are connected. If clock in source cannot be bound within one block, it means that the source comes from the other blocks. This information allows us to know what components are between clock source and IP clock. If there is a mux in the middle, the total number of cases where the IP clock can be controlled will increase according to the input count of the mux. Even in this case, the ACM should be known about all CME components related IP clock. The ACM provides debug information to enable log analysis for clock debugging. This slide shows the result of simply sorting the IP clock to debug to the module name using the text editor. So we can know how the IP clock changes at a glance, and we can check where it is unexpected IP clock frequencies. We didn't use any script for clock debugging through the ACM log. In our case, fortunately all frequency mismatches were software setting issue, not IT bugs. However, we think IT bugs can be indirectly detected through the case that the target frequency cannot be generated with any divide ratio or box selection combination, or even if any combination is there, it may affect the other IP clocks. Each unit ACM has 3 internal checkers so that easily checks the clock for various usages. The one frequency check task checks if the clock matches the target frequency when it called once. It usually uses when it checks if the desired frequency comes out after setting the clock control registers. Meanwhile, the wrong frequency check task checks whether the clock is maintained at the target frequency from the moment of test call. It's useful when verifying the clock whose value should not be changed. Finally, array frequency check task can be used to check if a series of target frequencies are covered. For example, if a target frequency argument has 3 target frequencies, it checks if the clock is generated once for all 3 frequencies. So unlike the other 2 checkers, when the scenario is over, it's necessary to check if the all target frequencies are touched through the get result task. These checkers allow the ACM to be used in various SOC verification as well as dynamic IP clock verification. The users do not need to make clock checkers or interfaces for clock verification for their blocks. In case of this dynamic IP clock verification, only one frequency check task was used. This diagram shows the verification flow of dynamic IP clock verification depending on DFS level. This verification requires a lot of iteration because it's inevitable to check the numerous IP clock frequencies according to the DFS level and the number of IPs in SOC. The ACM is used to reduce debugging time to solve this issue. Automated test bench generation is one of the efficient methods in SOC verification. The 3 files are used here for automation. Both CMU setting sequence file means dynamic frequency sequence, which is including clock logic setting values and orders depending on DFS level. It's used for making DFS scenarios. Second, sign-off specification includes the target frequency values of each IP according to dynamic frequency level. It's used for making IP clock checkers. Lastly, clock info includes the tree information and CMU components of each block clock logics. It's for the relationship CMU components and IP clock, and it's used for binding the active clock monitors. CMU setting sequence and clock input files are generated by CMU RTA generator, and sign-up specification is delivered from the design team. These three input files are used for automated test bench generation. Here is the experimental result. This table shows the comparison result of the simulation time and debug points between waveform-based debugging and logo-based debugging. The simulation time result is normalized based on the without the ACM. The simulation time with the ACM shows a time reduction of 66% on full chip simulation, because if we use the ACM, we don't need to dump the waveform. Meanwhile, the target debugging point shows the number of CMU component traced for clock debugging. It depends on the total number of CMU components in associated block design. In case of log-based debugging with the ACM, the target debugging point is only 1. It means we can debug the clock issue through the clock debug information in the log at a glance. It results in reduced debug time because it has no waveform trace time. In our case, the number of target IP clock is 1748. This number will be increased according to the number of the DFS levels. If it has 3 levels, the total number of clock corners will be 5244. It means even if clock errors occur under 1%, 52 IP clock issues should be analyzed. The log-based debugging for the clock is useful in this case. So let me summarize. These advantages will further increase verification efficiency as the simulation repeats with frequent DUT and test bench updates. In this paper, I introduced the efficient clock debugging method for dynamic IP clock frequency verification. The main goal of the proposed DHCM is to prevent waveform dumping that takes a long time and to easily identify key information related to the clock to reduce debug time. First, this can be used in overall SOC verification since the clock debugging is required in any verification. This is the conclusion of my presentation. Thank you for listening.